I've written down the results that we have obtained in the last class. Can you hear me properly? Can somebody unmute and say yes or
Yes,
no?
sir. Yes, sir.
The last time we there was a question. I'll go back to this a little later. First, let me answer the question. The question was that, if I understood correctly, the question was essentially regarding the particle nature and wave nature of the particle. And the particle nature is essentially signified by the fact that it has a specific position when it's observed. The wave nature, on the other hand, is signified by a say the diffraction, the interference, and that kind of activities when you see some kind of a wavy picture on a screen. Now, let us take, for example, the double slit experiment, where you have a, a plate with double slits here, and here there is a plate. So from here, uh, the electrons or photons or whatever go, and finally, when let's talk about electrons, when they finally fall on this plate, uh, then you see some pattern emerging in what form? Emerging in the form of discrete dots. So uh, they form discrete dots in a form that ultimately shows a kind of a structure. Now, why do they have discrete dots? Because each individual electron fell at a point, and if it is something like a, earlier there was the cathode ray tubes in the television, there the electrons would hit a fluorescent material at the tube surface, and that would light it, and that is where you see. So a specific dot, a specific place where the electron hit, and therefore you know that it's localized. So when an electron hits a particular point, it gets lit, or if it is a silver plate, as photography used to be done in the olden times, the silver gets some kind of a reaction happens when electron falls on it, and that can be ultimately seen by darkening of the plate. So you know that where it happened is localized. So when a particular dot happened, you know that it signifies the particle character, while the whole thing shows a wave character. So the wave character is exhibited by the overall appearance of the distribution of dots, and the particle character is characterized by each individual dot. Now, why do they distribute in this particular way? Because they follow a wave function. The probability of falling in different places follow a wave function, and when there are two possible ways of going through, then they will interfere, and ultimately there will be some places where the electron is more likely to fall. There will be some places where they will be less likely to fall, and ultimately when the pattern emerges, it is because of that. Now, the way the Copenhagen interpretation of quantum mechanics goes, uh, this interpretation says that the particle actually actualizes. It has a probability distribution. It's not localized in any place until you make an observation. It is actually at a distributed place, but in one place, it ultimately, when it interacts with something that is macroscopic, resulting uh, in an effect that is irreversible, then it takes a decision regarding where to actualize, and that happens according to the probability distribution given by the way. So One electron will fall here, another electron will fall here, a third electron will fall here, but they're all guided by the same wave function because they're different probability distributions, and according to the probability they will actualize in different places, and that is actually what we see as the wave character. So the electron has a wave character, light has a wave character, every particle has a wave character, and in fact elephants and me and you, we all have wave characters, but the wave character is in this case is in such large macroscopic bodies is so insignificant that we can forget about it, and we think we sort of look at ourselves, look at the things around us, look at cricket balls, and we tend to believe that the positions are always localized, but it's actually not so. Positions become localized when the particle interacts with something else, something external to the system, and in such a way that the result is irreversible. Then it actually takes a decision as to where to appear, and the moment that happens, the position collapses to that particular position, that particular value. So wave function collapses to that particular. In case of the Stern-Gerlach apparatus, you have a Stern-Gerlach apparatus oriented in a particular direction, which means the z direction is the direction in which the magnetic field is, and then you have allowed it to pass, but then you have placed a blockage here and allowed the other one. The moment you place a blockage here, you basically make an observation, because there will be some particles that fall on it and that get stopped there, resulting in something that is irreversible, and the other part goes through. And when that happens, then the wave function actually collapses, and this wave function actually becomes up. So this was a linear combination of both the possibilities of up and down in the z direction. So when it comes, it has a linear superposition. But here we have made an observation, and as a result of that, it has collapsed to a state. But now Stern-Gerlach apparatus is a apparatus where you do not have to completely stop the particle, as in case of a silver plate or something like that. In this case, the silver atoms actually go through and in a particular state. Okay. Now this is the Copenhagen interpretation, where we do not talk about a particular atom going in a particular path and falling in a particular place. Another particular atom going through another particular path and going through a particular place. We do not talk about which slit it went through, because it has probabilities of going through both the slits, and it is actually like a wave front that is traveling. And finally, when the wave reaches here, then it is distributed. It's not something that is localized. It's distributed. The particle is distributed over a range of space with different probabilities of being in different parts of this x coordinate, and ultimately it actualizes in a particular place when it is forced to actualize, when it interacts with something else. Is the point clear now? Because we have learned that if you have identical particles, indistinguishable particles, the words identical and indistinguishable, non-distinguishable are same thing, synonyms. So if the particles are non-distinguishable, then the way we try to construct eigenfunctions to represent a pair of particles is that we try to see that if I swap the indices here, 1 and 2, particle 1 and particle, if you swap them, then that should lead to the same wave function or the same spin state. And proceeding that way, we concluded there are two possible ways of representing the spatial wave function. One is with a plus sign here, and there is a minus sign and minus sign. And if it is plus, then the resulting wave function is symmetric, and that means if you swap, then you get the same thing. And if there is a minus sign, you get antisymmetric, which means if you swap, then you get minus of what it was. So these are the two ways that we have identified that we can have a spatial combined wave function. Uh, when we came to spin, we found that if we represent the spins this way, then if both are up or if both are down, then that results in a symmetric spin state, combined spin state. And also, when one is up, another is down, then there are two possible ways of writing it. One of them, this one with the plus here, leads to a symmetric state, and the other one, the minus here, leads to an anti-symmetric state. And since there are three possible ways by which you can construct a symmetric spin state, this is called triplet. And this is called a singlet. So there's only one way of constructing an antisymmetry. By the way, yesterday when I was writing, I did not put the normalization factor. Of course, if you just add these two, it will not be normalized. You have to divide by root 2. Same here. So these three are the triplet states, and these is the singlet state. Now let us try to figure out the effect of applying operating with a operator. Say the operator for the z coordinate z component of the spin was sz operator. Now we need to talk about which particle I'm talking about. So this is the particle 1. Suppose this is the spin component, observer of the spin component of particle 1 in the z direction. Then if I apply that onto this, so this operator is operating on the joint spin state. Then since it is the operator for the first particle, then it will operate only on the first particle and will do nothing to the second particle. So we can write it as a bracket SZ1 operating on the first particle, leaving the second particle undisturbed. Okay, and the result of this is we know that it is h cross by 2. So it is h cross by 2 up first one and up second. So we see that for this operator, this is an eigenvector. This is actually the same, h cross by 2 up down. So this is an eigenvector with an eigenvalue h cross by 2. Okay. Similarly, if you have sz of the second particle, again applying on up. Oh, sorry, I operated on up down. I wanted to operate on up. I'm taking that. Sorry. So up, yeah, through up. Then if I apply the second one on up, if I apply the second one on up, in the same way we'll proceed. We'll get same h cross by 2, again up. Okay. So if I now ask, what is the total angular momentum in the z direction, then we will have to do it by writing sz1 plus sz2. This applying on up, and obviously these two added together will get h cross up. So the total angular momentum in the z direction, that operator has an eigenvalue h cross, and the eigenvector up. You can do things similarly. You can do things for the up, down, 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 up, and all that. So then similarly, we can also obtain, and get some space here, operating, proceeding exactly in the similar way, we see SZ1 operating on, now this time we will operate on up, down, up, down. Then you see that the down part, it will not operate on, it will operate only on the up part. Exactly the same result will pattern. So you will get h cross by 2 up, down, right? Similarly, if it is SZ2 operating on up, down, then it will leave this one undisturbed. So the first one will, but second one, if the eigenvalue will be minus h cross by 2, so minus h cross by 2 will come out. Again, it will be up. So the up, down is also an eigenfunction of this, and similarly we can proceed. SZ1 on say down, up, it will SZ1, and therefore it is an operator related to the first particle, and it is down, and so this will result in minus h cross by 2 down, up. Okay. So why is exhausted everything? Z2 of this was up, down, this is down, up. Z2 down, up will be, since it will operate only on the second one, which is up, therefore it is h cross by 2. Now, if that is so, then you see that the combined operator, the total operator operating on, say, operating on, say, this one, it is up, down plus down, up. So this is operating on up, down plus down, up is equal to, you notice that last h cross by 2 and minus h cross by 2 cancel off, and therefore you get 0, and the 0 we can write as 0 multiplied by up, down plus down, up, which means that this is also a eigenvector of this operator with eigenvalue 0. Okay. Similarly, we get the same thing for SZ1 plus SZ2 operating on the minus 1. Up, down, minus, down, sorry. This will also be 0 because of this plus and minus will cancel off, times the same. So this implies that this is also an eigenfunction of the combined angular momentum operator with eigenvalue 0 and eigenfunction 0. So let us summarize a bit. Let me delete some.
Excuse me, sir.
Yeah.
So, but having an eigenvalue of 0, isn't that like a trivial case? Won't that hold true for every vector, even vectors apart from this?
Why?
So,
Because here an operator operating on some kind of vector will give the vector times something. That something will not always be 0. Only in this case, because it was one was h cross by 2, another was minus h cross by 2. Therefore, they cancelled off.
okay, sir.
Huh? Okay, let's go up, get some space. Yeah. So let me summarize then the results that we are getting. We get the total operator operating on down. If we do that, you will again get a minus h cross. The way we got the plus h cross is in the up direction. Okay, so this is, I'm not doing it, it's trivial, but we have seen that what happens. So we have already got sz operating on up is h cross. Now, if you recall, when we had one particle, then the sz operating on that one particle was giving a ms times times the eigenvalue was some ms times h cross. Okay, in this case also, when we are considering two particles, we can imagine the same way. So this we can say, this is in this case, since there are two particles, multiple particles, you cannot use the same notation. Earlier we use small ms. We can use the capital M subscript s times h cross. This one is the eigenvalue with ms is equal to 1. Okay, and in this case, ms times h cross with ms equal to minus 1. So you see that there is a equivalence of the magnetic quantum or spin magnetic quantum number that we have earlier obtained for single particle. We are getting something similar to that in case of multiple particle, but when it is down, the value of this is minus 1. When it is up, then the value is plus 1. And when it is for the other state that we have already written, this one, 1 by root 2 up, down, plus, down, up. For this one, when sz operates, that means sz1 plus sz2 operates, we have found that it is 0. So this ms will be equal to 0. 0 times h cross ms equal to 0. So we have found that there is a way of identifying the magnetic quantum number for a couple of particles. And that means the combined magnetic quantum number, which we are representing by capital MS. And in these three cases, we have found that these are 0, and also for the singlet case for 1 by root 2, this is up, down, minus, down, up. Then also m is equal to 0. Again, this h equals by 2 cancels off. So all these 4 cases, we have been able to identify the spin magnetic quantum number, the joint spin magnetic quantum of the system. Now, we have already seen that whenever we were talking about the orbital angular momentum, we were talking about the operator L square. Whenever we were talking about the spin of individual particle, we are talking about the operator S square. In a similar way, we can ask what is the S square operator, the square of the total spin operator for the couple of particles. Now, I'll not go through the elaborate proof. All that happens is that the result is exactly the same. So, these, the ones that we have already identified, these are also eigenvectors of S operator square with eigenvalues again exactly same way, S plus 1 H cross square, but in this case we are writing capital S. This is capital S, so let me capital, because we are now talking about the combined spin of the two particles. So this is S plus 1 H cross square. The way we have seen in case of orbital angular moment, it was L plus 1 H cross square, or in spin S plus 1 H cross square. Here also the same thing happens. Only thing is that the S with S equal to 1 for the symmetric ones, triplet states, that means symmetric states. Right? And S equal to 0 for the singlet state, this is antisymmetry. Okay, let me summarize, because all this is a bit, might be a bit difficult to memorize or remember. So let me summarize what we've got. What we've got is that we have obtained certain possible ways of representing a couple of particles, because we know that they are identical, they are non-distinguishable, and these are the possible ways. And we have found that when each one of them operates, then we can get the eigenvectors, and these become the eigenfunctions. And similarly, when the total spin operator operates, we get eigenvalues, and these eigenvalues are expressed in terms of ms h cross, thereby giving the spin magnetic quantum number as -1, +1, or 0 for the three triplet states. That means the symmetric. For the singlet state, that's antisymmetric, it becomes 0, and the S value, the spin, total spin of the coupled system, can be either 1 or 0. By the way, for this, for a spin half system, so either 1 or 0. For the triplet state, it is +1, and for this antisymmetric state, the singlet state, it is 0. Now you might have noticed that we were always abbreviating our notations. And let me delete this space. We've always been abbreviating our notations, but these are a bit longish. Yeah, any question?
Sir,
Yeah.
so the spin quantum number is different, it's discrete for different particles, right?
Spin quantum number is
Discrete for different particles.
Well, we are now talking about spin half particles like electrons.
Yeah.
And this spin quantum number S for electrons, pair of electrons would be either +1 or 0.
But here it is 0 and 1.
Yeah, either +1 or 0. See,
Yeah, I mean,
there are
not
two
so.
particles. See, each particle has a spin of half.
Yeah.
So, if there are two particles, uh, if you actually work out the whole detailed mathematics for the S square, because that's quite long. I mean, it will take a year, take a whole class to do that. That's why I just avoided. You can get in any book. The point is that if you operate with that on a eigenfunction like this, you get 1 as the eigenvalue. And if you operate with this, with the singular state, you get 0 as the eigenvalue.
So my
Therefore,
question is,
yeah.
the photons also have S equals to 1.
No. I'm not going to photons at all yet. Today, I'm
Okay.
talking on spin-half particles. I will have special classes devoted to photons. Okay.
Okay.
Photons have spin of 1. One photon has spin of 1. But here we are talking about 2 electrons or 2 neutrons or 2 protons. Okay. They together can have only these two values of the total spin, either 1 or 0.
Okay.
Okay. We are not talking about photons yet because photons have spin of 1. Yes, I'll come to that.
Okay. Okay.
Now, we have seen that always we have been abbreviating the or writing shorthand by taking advantage of the bracket notation, and here these are a bit unwieldy, a bit longish. But if we can write a ket of S and MS, just this, then that uniquely can specify each of these states. Okay. Uh, if you operate on that by h square, then it will be, in some cases it will be ms h cross. No, it will be s plus 1, s plus 1 h cross square, and the same thing s ms. And if you apply sz on the same thing s ms, you get depending on this, you get ms h cross. Ms would be different for different cases, multiplied by the same thing. So you see, these are the eigenvalue equations then, and this can be nicely represent each of these states. So just let me clarify. The triplet states, triplet means 3 possible symmetric states. The triplet states will then be written as, there were 3 triplet states, 1, up, up. That will be written as, its S is 1 and MS is also 1. There was a down, down state, one of the triplet states, that will be written as, S was 1 and the MS was -1. And the other one, 1 by root 2, up, down, plus, down, up. This will then be written as, again, the first one, S is 1, and this one is, this one was 0. MS was 0. So this uniquely specifies this state, and the single state would be single state is 1 by root 2. Sorry. Up, down, minus, down, up. That was a anti-symmetric state. it will be then written as then its S was 0, its MS was 0. So these are very brief, short ways of representing all the possible combined states of two spin half particles. Okay, so this is a nice way of writing things. So we have seen that when we consider two particles, identical particles, non-distinguishable particles, then spatially they can be distributed, they can be represented this way, these two possible ways, and the spin part can be written in these four possible ways. There is a symmetric, there is an antisymmetric, here also there is symmetric, there is antisymmetric. Now we need to put them together because ultimately a pair of particles is specified by their spatial distribution as well as the spin distribution. So we need to put them together. So the total, the when you put them together, then the psi 1 2, the total psi 1 2 will be then psi x1 x2 representing the combined spatial distribution state, and s, this is the total. The total. Now we have seen that this can be symmetric or antisymmetric, and this can also be symmetric or antisymmetric. What about the whole thing? Now, if you consider symmetric and antisymmetric functions and make products of them, then you know that certain rules immediately are apparent. One is that if one is symmetric, the other is also symmetric, the result has to be symmetric. So spatial symmetric, spin symmetric. Then the total is also symmetric. Remember, I told you that the total, the spin and the spatial part combined together, the total thing, whether it is symmetric or antisymmetric, will determine whether it's boson or fermion. A boson can only be in a symmetric state, total symmetric state. A fermion can only be in a total antisymmetric state, and therefore we need to understand this carefully. So the spatial antisymmetric and the spin symmetric, spin also antisymmetric. I'm not writing antisymmetric, just anti will mean the same thing. Spatial antisymmetric, spin antisymmetric, then the whole thing will also be symmetric. Spatial symmetric, spin anti, then the total will be anti. And finally, the spatial is anti, and the spin is symmetric, then the total is again antisymmetric. And the spatial symmetry can happen in one way. Spin symmetry can happen in three possible ways. Spatial antisymmetry can happen in one way. Spin antisymmetry can happen in one possible way. So a symmetric wave function can happen in uh, four possible ways. Spatial symmetry can happen in one way. Spin anti can happen in one way. So this is one possibility, and spatial anti-spin symmetric can happen in three possible ways. So this can also happen in four possible ways. So there are four possible combinations that can that a boson pair of bosons can have. There are four possible combinations that a pair of fermions can have. Okay. So for example, let me just exemplify, because electrons are so very important for every purpose. So we need to understand things for.
Excuse me, sir.
Yeah.
Sir, before erasing this,
Yeah.
sir, the new notation that you introduced here, SMS. Sir, MS is just we derived just now by operating S square
Right.
on
Right.
on
No, no, no.
these.
We have obtained MS by operating the SZ.
Yeah, sorry, SZ.
Yeah.
Sir, what was S, sir? I think I missed
Oh,
something there.
S was a part of the eigenvalue of the S square operator. When S square was operating, the eigenvalues come in the form of S plus 1 H cross square, and that S here we are talking about. Okay. In continuation with whatever we have done earlier for the orbital angular momentum, it was L. For spin angular momentum, it was S. And here also, for both the particles taken together, there will be some S. And that is this, obtained by operating S square as an operator on the state, and the eigenvalue comes in form of this S plus 1 H cross square. Okay. So the triplet states, let's consider the triplet state. We are considering now in what ways we can have, let me see, it is psi minus, which is a antisymmetric state, x1 comma x2, and then we consider 1 comma 1, and 1 comma 1 was the up state. So this is equal to 1 by root 2. It is psi n x1, psi k x2, psi minus, so it is minus psi k x1, psi n x2, bracket close, and this one is up. So both put together will give an antisymmetric state. Antisymmetric and symmetric, so it will give antisymmetric state. Yes. Psi minus x1 x2, and this one is 1 comma 0. To try to recall what was 1 comma 0, did I delete it? Sorry. 1 was for all the symmetric states, it is 1, and ms is 0. So that is actually I'll write it here. This is 1 by root 2. This thing, there was a 1 by root 2 here, there was another 1 by root 2 here, so it will become 1 by 2 actually. And it is up, down, plus down, up. Okay. And then you have psi minus x1 comma x2. It is 1 comma minus 1. Then it will be again 1 by root 2, this whole thing, because here we are writing the same thing. And here this is down, down. All these are possible states of a electron. Okay, because these are fermions. The total situation is antisymmetric. And if you take a singlet, then the possible state is like this: psi plus now x1 comma x2 combined with the singlet 0 0 is equal to this will get a 1 by root 2, this will get a 1 by root 2, so this will be half here. It is then plus psi n x1 psi k x2 plus psi k x1 psi n x2 close. Now this is the singlet state, so 1 by root 2 I have already taken up front. It is up, down, minus, down. So an electron can live, a pair of electrons can live only in these 4 states. I said that there are 4 ways of writing this fermion states. These are the 4 ways in which a fermion can live. Clear? Now, you might ask, what exactly then are bosons? What exactly then are fermions? Now, to give a very short answer, a boson is a particle with integer spin. So spin integer spin, integer valued spin. So that means s equal to 0, 1, 2, and fermions are half integer spins. Particles with half integer spin, and this would be s equal to half, 3 half, 5 half. So there are particles of all these types. Okay, electrons, protons, neutrons, all these are fermions. Photons are these alpha particles are bosons. Anyway. So we immediately conclude that if we put 2 fermions together of this type, then they can take only these states, nothing else. Okay, these 4 states. From this, you also notice that you might put multiple particles together. An atom is a combination of many particles. And the rule is that if you have an odd number of particles in an atom, odd number of fermions in an atom, then you get a fermion. But if you have an even number of fermions in an atom, then the whole atom becomes a boson. Okay, so combination of odd number of fermions gives a fermion, but combination of even number of fermions give a boson. So atoms, molecules, a large number of fermions can totally be a boson. For example, let's consider rubidium. Rubidium is 85 RB. here it is 37, which means that 37 protons, 37 electrons, and 85 minus 37 is equal to 48 neutrons, which means total number of particles would be even. So therefore, that rubidium atom is a boson. Why I talked about rubidium, I'll come to that later. But you can easily see that there will be many such atoms which will be bosons altogether, and there will be also many such atoms which will be fermions.